projects at the moment, so very busy.
Okay, okay. It seems the live stream has started.
Yep, it just gave me a notification.
Right. Shall we start? Prasanna, what do you say?
Yeah, just a moment. Just as it did last time, it's still not confirming on the YouTube channel if the live stream has begun.
All right. So just
yeah, so sorry about this. Just give me a minute more and then
sure.
Yeah, then I did get the notification on Zoom, but it's not clear whether it's started on YouTube or not. So.
Okay.
Yeah. Are you able to get questions from people on the live stream as well?
Yeah, you should be able to. No,
Yes.
actually not from the live stream. Live stream, you will not be able to get questions, whoever is attending the live stream.
Okay.
Meaning from YouTube, people can type their questions if they want to.
Yeah. Oh, okay.
Yeah. I was just thinking if it has a live chat there, you might want to monitor that for people asking questions.
Yeah. Yes, sure. I'll do that. I think the live stream has started.
All right, so shall we start then?
Sure.
Okay. All right, so good afternoon and evening, everyone, whichever applies to you. Today, our speaker is Professor Dominic Berry. So Professor Dominic Berry received his PhD from the University of Queensland in 2002 and has been at Macquarie University, Sydney since 2011. He was an ARC postdoctoral research fellow from 2004 to 2006 and an ARC future fellow from 2011 to 2015. He is currently funded by a sponsored research agreement with Google. His research in quantum algorithms has laid the foundations for many of the methods currently used in Hamiltonian simulation and quantum chemistry. This includes work from 2007 on product formulae, as well as methods using quantum walks and linear combinations of unitaries. All right, it's a pleasure to have him. And yeah, over to you, Dominic.
Okay, thank you. So what I'll be talking about here is some of the general methods that are used in Hamiltonian simulation and quantum chemistry now, and two particular results that we have, which are roughly illustrated on the left and right here. We have one which is designed for simulating the molecules, and another one which is designed for simulating periodic materials. It has a particular trick which is illustrated there, which I'll explain a little later in the talk. I've also mentioned a few people who are collaborators on this work, as Junho Lee at Columbia, Nathan at Toronto, and a whole bunch of people at Google, particularly Ryan Babush, who's the group leader there. So the motivation for these types of quantum algorithms is that, and just a moment, I think it's not responding to the advancing the slide. There we go. So it's essentially for solving for things where you might want to, say, design molecules or materials. So the illustrations here, well, in the middle, it's for battery technology. On the right, it's for the fertilizer production, catalyst for producing fertilizer. And then on the left, it's the drug discovery. So we have mainly the battery and fertilizer applications in mind. There's some other papers where people have talked about drug discovery. Now, when you're looking at simulating these types of things classically, you find that if you're simulating something that's small, then it's fairly rapid to work out its properties. But as you're going to larger and larger systems, it's rapidly becoming intractable just because of the exponential state space. And what's illustrated on the right there is the FOMOCO active site, which is what's involved in biological nitrogen fixing. So that has a large number of atoms, and what's also important there is it has the heavier atoms like iron and molybdenum. And it's found that when you have the heavier atoms, you tend to have a much larger state space, which is making it hard to simulate. Now, when you're talking about simulation, the more abstract problem is Hamiltonian simulation. So often what you're trying to work out there is how to simulate the evolution under the Hamiltonian. So the initial work on that topic was, well, there was also the first work by Seth Lloyd back in the mid-90s, which was just looking at a simple Trotter product formula. Then later we were looking at the more advanced higher order product formulas applied to the quantum simulation. Then we later developed methods based on quantum walks, linear combinations of unitaries, and we're applying that to Taylor series. And then there was some further proposals by Guanghao Lo on quantum signal processing and what's called qubitization, and also using the interaction picture to give further improvements. And that's for more the abstract problem of Hamiltonian simulation. But when you're talking about how to do things for quantum chemistry, that introduces all its own the particular difficulties. So we've done a whole lot of work on improving the specific case of quantum chemistry. So one which is mentioned up the top there, which is actually useful more generally, is for doing direct phase estimation on a step of a quantum walk. And that is able to solve the problem that you're often interested in quantum chemistry of finding energy eigenvalues while avoiding the need to generate the actual Hamiltonian evolution for the time evolution of the system, which tends to be more difficult. There was also this method of working out QROM, which was presented by Lokalishnikov and Schaefer. And we also have some other variations of that to get further improvements. So the idea of QROM is it's sort of a more practical variation of QRAM. So the idea of QROM is essentially you're working out a sequence of gates in order to input classical data into a quantum algorithm, which is often needed in quantum chemistry because there's some pre-calculated classical information that you're wanting to input into your algorithm. Another method here is coherent alias sampling, which is something that we use for state preparation. Then we also have a whole bunch of different methods of representing the Hamiltonian, which is essentially items 4 to 7 here. So we were looking at things in terms of sparse Hamiltonian. We also mentioned double factorization in that paper, which was elaborated on more by the von Berg et al. Paper, which found some quite nice improvements. And then we looked at the tensor hypercontraction representation in our work, which gave us a whole lot more improvements. And then we also developed methods using the plane waves representation, which is appropriate for periodic materials. So it's mainly, after going over the general methods, I'll talk about the tensor hypercontraction and plane waves. So the main results coming from this is that on the left here, the tensor hypercontraction is giving you something that's suitable for molecules which use a Gaussian basis, which is essentially a basis of orbitals for representing the molecule, which are calculated in advance classically. So this is where you have a large amount of data which has been pre-calculated classically. But the advantage of this is that the number of orbitals that you need is relatively small. And then the tensor hypercontraction is able to give a compact representation of the Hamiltonian, which uses a smaller amount of data than you might naively expect based on the amount of data that you're initially given based on the pre-calculation. And our estimate of the gate counts beats all prior methods for the simulation of molecules. Then on the right, we have the plane wave basis, which is what you're using for periodic materials. And the advantage of that is that it uses a much smaller amount of data because it's essentially just going from a set of orbitals which are plane waves. So you can essentially calculate everything on the fly with these. But the disadvantage is that you need a very large number of orbitals to give the same precision as you'd be getting with the Gaussian basis. So this one, it is possible to use it for molecules, but it's also difficult to know how many plane waves you would need to get a similar accuracy as for the Gaussian basis. But it's expected that it's going to be very efficient for things where it's periodic, because sort of if you have a periodic material, that's a natural application where you would use something like plane waves. Now, there's a couple of approaches that you can use. You can use a direct cubitization, which is terminology I'll explain in a moment. And you can also use the interaction picture, which is a more advanced method. And then we have a whole lot of algorithmic improvements, which would give roughly a 1,000-fold speed up for a realistic parameters. And so then sort of the estimated calculation speed, well, for both of these cases would seem a plausible, provided you're able to build a full fault-tolerant quantum computer. So this would need to be something which has error correction for the storage of the qubits, and it would also need a magic state factories in order to do your non-Clifford gates. And that's more difficult than just being able to store store data. So this is why it's called a fault. Sorry, I'm forgetting the exact terminology. Anyway, so going on to the general methods of Hamiltonian simulation, the first one here is just Trotter, or it's better described as Lee Trotter. I often call it Trotter, but this is something that was first invented by Lee. Now, the simplest case would be just if you're approximating evolution under a Hamiltonian that's A plus B, and approximate it as a product of evolution under B followed by evolution under A. Now, this is something which would be exact if you were talking about just a real or a complex numbers, but the A and B here are operators or equivalently matrices, and this is not exact. It's going to be approximate if T is small here. And then in the general case where you're wanting longer times, you would break that longer time up into many short times and use R repetitions of that shorter time. Then if you're wanting to get a more accurate approximation, you can use an approximation that looks like this here, where you have spread out the evolution under A on both sides of the B, and you can generate arbitrarily high order approximations using an iteration like this, which was invented by Suzuki. Now, it's also possible to generate higher order product formulae with more complicated procedures, and we have a paper out on that fairly recently. Now, a more advanced approach than product formulae is using linear combinations of unitaries. So the general idea here is that you have a unitary that you would want to apply, which is given as a sum of simpler unitaries. So this is quite a different type of scenario than you'd typically come across in quantum computing, where you have a unitary which you're implementing via a product of unitaries. And quantum computing, it naturally gives you products of things and not sums of things. But the linear combination of unitaries perspective is essentially using controlled operations to try and generate a sum. So if you have a control register, which is indicated by the top line on the left here, you would use an operation P to prepare a superposition state which has amplitudes going according to square roots of the weights in the sum. Then you do a controlled UL, invert that preparation, and if you're able to project onto zero, you would get the target unitary applied to the target system. And something that's very important here is this sum over the weights. And this will essentially be governing what the probability of getting the correct measurement result is. And in typical cases, you're not going to have unit probability of a success here. But what you can do is what's called oblivious amplitude amplification, where you're doing the whole procedure many times with a reflection about the zero state interleaved. So the thing in the dotted box here is essentially what we had on the previous slide. And actually what's drawn here is intended for a self-inverse UL. If the UL isn't self-inverse, you need a UL dagger in the middle. But the general idea of this is that you're able to amplify to get the unitary operation U without having to reflect on that initial state psi. So this is why it's called oblivious, because it's oblivious to what that input state is. And this is also what you need if you're aiming to do this with some particular input state and then perform a sequence of different unitaries that are all generated by this procedure. So if you're doing that, you need to be able to do this oblivious amplitude amplification. Now, and another thing which is closely related is what's called qubitization. And this is essentially looking a lot like what you would have it as the steps in the oblivious amplitude amplification. So you see here, you have your P and a controlled HL now, and then a P dagger and then an R. So this is a lot like what we had as the steps here, but here we've bundled things together into a single step with the reflection as well. And we're also taking an HL, which would be a unitary operation. But now what we're doing is summing things to get a Hamiltonian rather than a unitary. Now, if we're doing this, this is a bit of a different scenario to before, because you can generate a unitary on a input state deterministically, because unitaries preserve the amplitude, but you can't apply an H to a general input state deterministically, because typically there's going to be various amplitudes resulting on different initial states. But what we're going to do here is actually look at the eigenvalues of this particular operation that you've generated. And it turns out that if you look at the complex plane, that for each eigenvalue little h of your Hamiltonian, you're actually generating two eigenvalues of this operator, which is often called a qubitized operator. So it's also scaled by this lambda value, which is this sum over WLs. So what you're finding now is that you have an operator which has eigenvalues which are just a simple function of the eigenvalues of the Hamiltonian. Now, if you want to know what the eigenvalues of the Hamiltonian are, then you can do phase estimation on this walk operator. Does someone have a question there? No? Okay. Sorry? Okay, I'll just continue then. So the idea is you want to do phase estimation on this walk operator, and then that will give you an eigenvalue of the walk operator. It might be sort of the one to the left or the one to the right of the complex plane. But regardless of that, you can invert the function to work out what the original eigenvalue of the Hamiltonian is. And so you don't need to generate the evolution under the Hamiltonian. You can just do the phase estimation on this walk operator. Now, another thing which you can do, which is useful for the case where you actually want to generate the time evolution, is a Taylor series. So the idea here is, well, you have your Hamiltonian, which is written as a sum of unitaries again, but you're going to write your evolution under the Hamiltonian as a Taylor series. So it's a sum over various powers of the minus IHT. And this is going to be working for small t again. This is going to be a similar idea as what you have for product formulae, in that you want to break your evolution up into a bunch of shorter times and use an approximation that's suitable for short times on the individual steps. Now, this sum for the Taylor series, you can plug in that sum over the HLs for the H, and then you're going to get a complete expression, which is a sum with various weights of various products of the unitaries HL. Now, this is, again, a form of a linear combination of unitaries, except you have sort of a more complicated sum here with the sum over K, a sum over L1 up to the LK and so forth. But this is, again, something which can be done in this scenario we had for a linear combination of unitaries, where you have a preparation, a controlled operation, and an inverse preparation. And by doing that, combined with the oblivious amplitude amplification for a linear combination of unitaries, we were able to show that the complexity would scale like an H lambda norm. So we're just using this to describe the lambda, which is like the sum over weights of the linear combination of unitaries. It'd be like the sum over alpha L's here. Times a time, times a multiplicative factor in the log 1 over epsilon. So that gives you a quite a nice complexity for simulating time evolution. Now, this is something which can be generalized to the case of time-dependent Hamiltonians. So for time-dependent Hamiltonians, your Taylor series, which you would have here, gets turned into a Dyson series. So a Dyson series, you have a whole lot of integrals over time. So you see here, it's saying you have a sum over K, which is the same as we have over here. But then you have an integral over 0 to t of a t1, and then an integral over t2, which is dependent on the t1. And each successive integral over a t is dependent on the value, the range is dependent on the value of the previous one. So when you're looking at this sequence of H Hamiltonian evaluated at the various times, you actually have a time ordering here. And this way that it's restricted with the range of the integrals is actually the reason why you don't have a 1 over k factorial, which is what you have over here. You could also write this in terms of a 1 over k factorial and have all of these integrals over the times over the full range of 0 to t, but then you'd have to be doing a time ordering on these, and it's more convenient to write it out in this form. Now, this is something where you can again use a linear combination of unitaries approach, but now you have to have a much more complicated scheme where you're needing to prepare superpositions over discretized times to discretize these integrals. Now, it turns out that when you're doing a linear combination of unitaries, it's actually possible to do essentially discretized integrals with a complexity which is only logarithmic in the number of terms in the sum, which is something you might at first think's impossible, because that would seem to be sort of violating some no-go results. But the reason why it's actually possible here is that this is only occurring in the actual operation which is being applied. You'd never actually classically evaluate the result of a discretized integral. And then using these discretized integrals and then some schemes with a quantum sorts of times, you end up with a similar complexity as you would get for the case of the time-independent case. Now, this is something which we worked out in our paper back in, well, the archive version was released in 2018, and Guanghao Lo and Nathan Weeb simultaneously worked out a similar result, and they also applied this to the case of using the interaction picture, which is very neat. So for the interaction picture, this is now looking at the case of the time-independent Hamiltonian again. But for the interaction picture, you artificially construct a time-dependent Hamiltonian by rotating one term according to the frame of the other term. So when your Hamiltonian is A plus B, you define a new time-dependent B according to a rotation under e to the iat. And when you do that and plug that into your Dyson series implementation of a time-dependent evolution, you get an overall expression that looks like this. So you can see here that you have for order k in this sum, you're again having this ordered sequence of integrals over time. And then you have a product of operators here where you have the b many times interspersed with evolution under A. And this is incorporating sort of the extra parts that are needed to actually give the time evolution. And then when you look at the cost of this overall simulation, you're getting a cost of the linear combination of unitaries application of B plus a cost of applying this evolution under A, and then that's multiplied by the norm of B for the number of steps of amplitude amplification you're going to need to use for the linear combination of unitaries. Now, this is quite different to what you would normally expect in something like a Taylor series, because here you would normally be expecting that the number of steps that you're going to need is going like the norm of the entire Hamiltonian, at least according to this lambda norm. But in the interaction picture, you could have an A here, which has a very large norm, and a V and a B with a very small norm, and get an overall complexity which is going like the norm of this B, which is much smaller. And that's the advantage of the interaction picture, is that you're just paying the cost according to the smaller part. And A might have a large norm, but since you're just evolving according to the e to the minus iat, if you can do that efficiently, you're not really paying that cost of the norm of A. Okay, so that's on the more general Hamiltonian simulation methods. And next I'll go on to talking about the applications to quantum chemistry. So the representation of chemistry is using what's known as orbitals. So if you're familiar with, say, the solutions for the electron around the nucleus for just a hydrogen atom, say, if you remember that, you have these rather complicated patterns of lobes according to special functions. Now, that is something which can be worked out far more generally for combinations of multiple nuclei. So you get things that look like this, for example. So sort of this is intended on the right here as 4 alternative possible orbitals for the I think that's indicating 3 nuclei there. So how you can express your state of your system now is that each of these possible orbitals might be occupied by an electron or not occupied by an electron. And so according to the exclusion principle, each orbital can only have one electron, except for, of course, spin. You can have a spin up and a spin down. And this is much the same as you might be familiar with for the hydrogen atom. But for these more general systems, what you want to do is describe it by a Hamiltonian that looks like this. So you have this thing here on the left, which has two annihilation operators and two creation operators. And these are fermionic annihilation and creation operators for electrons. So because they're fermionic, they have anti-commutation relations rather than commutation relations, which you'd get for the just photons. And you have, when you have these combinations of two annihilation, two creation operators, it's essentially telling you that that two electrons are hopping from one orbital to another at the same time. And physically what that means is it's like corresponding to a interaction between two electrons that is coming from, say, a inter-electron potential energy. The thing on the right-hand side, you see you've got an A dagger and an A, and there's only two of them, there's not four. So that's telling you you just have a single electron going from one orbital to another. And that can correspond to, say, just a potential energy as would be coming from a nucleus. And here, this is assuming that the nucleus is treated classically. You're just assuming some fixed positions for the nuclei and working out the electronic wave function. Now, it also has these weights here. So you see you've got an HPQ and an HPQRS. And these are calculated from these rather complicated integrals in terms of the orbitals which are dependent on position. So these are integrals which you would typically not be wanting to compute on your quantum computer. We did put out a paper where we were looking at on-the-fly methods of calculating these integrals, but we think that's likely to be it's likely to be less efficient than actually doing it with pre-calculation of these things. Now, with the pre-calculation, there's difficulties because, well, this is 4 indices here. So essentially the number of these HPQRSs is going to be going like n to the power of 4. Now, typically this n for classically intractable examples, it might be, say, 100 or 150. Now, even if it's only 100, if you have n to the power of 4, 100 to the power of 4 is going like 100 million. So even with taking account of various symmetries, that's indicating that you might need millions of classically pre-calculated numbers to feed into your quantum algorithm. And you're going to pay a cost in gates for every piece of classical data that you're feeding in. And you're not just needing to feed that in right at the beginning. You're going to have to feed that in lots and lots of steps of your quantum algorithm. And essentially, this is what's happening. If you remember before when I was talking about linear combination of unitaries, in that P operation for preparing the superposition state, you're going to need to feed that data into that operation. And that is going to need to be done many, many times. So this is really an important cost which you want to reduce as much as possible. And that's why you want to have more compact representations of these Hamiltonians that isn't sort of just the explicit listing of every possible HPQRS. So, so this slide's just talking about what I was saying before, that you're needing to pre-calculate things to feed into the P. And another feature of these types of algorithms is that we're distinguishing between Clifford gates and non-Clifford gates. So the Clifford gates tend to be things like the NOT gate and the CNOT gate, and they're easy to do in the surface code, and the surface code is really the most practical proposal still for what you might do in sort of a planar network of qubits, like, say, Google and IBM are trying to build. And the problem with Clifford gates is that even though they're relatively easy to do in this fault-tolerant way, the full quantum computation actually needs non-Clifford gates as well. And there's various results telling you that if you were to just use Clifford gates, then the whole thing could be classically simulated. So you don't expect that your quantum algorithm would ever be doable with just Clifford gates, and that you are going to need some non-Clifford gates. And the non-Clifford gates are constructed by these very complicated procedures, which is illustrated in the lower right there. And so these tend to have a far higher cost than doing the Clifford gates. And so we tend to want to count the cost of these. The most important non-Clifford gate that we're interested in is the Toffoli gates. And so we're particularly counting the numbers of Toffolis. And overall, what we find is that the Toffoli complexity tends to go like the lambda value, which is like that sum over weights that I was explaining before. And that'd be like typically the sum over HPQRS is here, and multiplied by the square root of the amount of data in the Hamiltonian. So even though the overall gate complexity might be going like the total number of items of data, the Toffoli complexity would be going like the square root of the amount of data, which can indicate that you're getting something a bit better in terms of the realistic scaling than just the number of items of data. Though I should emphasize that the amount of data is the number of items of data and the number of bits in each of the items. So there's like, it's not just a number of items. So overall, what we'd like to be able to do is reduce the amount of data that's being used to represent the Hamiltonian still. So just keeping an eye on the time, I might briefly mention the coherent alias sampling. So the coherent alias sampling is essentially how we're feeding the data into the quantum algorithm in order to do that state preparation. So the general idea is that you have a equal superposition state, and then you are using this superposition over L to output some data that's dependent on L, which we're calling alt and keep here. But these are actually things that are going to be computed from parameters in the Hamiltonian. And the coherent alias sampling is essentially telling you that you can swap the L and alt L register with a probability that's based on the keep L. So this is done with including an extra superposition register, an inequality test, and a controlled swap. And the state that you're going to prepare will then end up having the amplitudes according to this root WL, which is what you want. And to generate these L-dependent data in this superposition, this is what the quantum ROM is for. So on the left here, what's being indicated is that you have some L stored in some register, and then you're outputting some L-dependent data. Now, the brute force way of doing this would be to say, okay, I'm going to check is L equal to 0, and I'm going to check is L equal to 1, then is L equal to 2, and so forth. Now, checking, say, L equal to 0 is a multiply controlled Toffoli. So remember, a toffoli is something which is, it's a bit like a generalization of a C-naught. You're going to be taking, instead of a single control, you're going to be taking two controls for a toffoli. So it's like a doubly controlled C-naught. Then a multiply controlled toffoli is now using more controls. And if you're controlling on all zeros, and that's essentially saying, if my L value is 0, I'm going to be outputting some L-dependent data. And a multiply controlled toffoli can be constructed in terms of multiple toffolis. So this QROM is actually saying we're going to control on 0, construct that from toffolis, control on 1, construct that from toffolis, and so forth. But then you can actually cancel a whole lot of toffolis in between these successive multiply controlled toffolis, and you end up with something that looks like this. And these things where you see sort of left elbows or right elbows, these are essentially taking an input zeroed state and doing a toffoli, or doing a toffoli so that the resulting state would be zeroed. And sort of it's just drawn like that to indicate that you're just introducing an ancilla at that stage, or you're going to be discarding an ancilla. And these like circles with question marks here, these are indicating C-naughts which might or might not be applied depending on what your data is. And this is sort of a nice way of constructing quantum ROM, but then there's this more advanced version which was invented by Low, Kalichnikov and Schaefer, which is able to give a complexity which is roughly going like a toffoli complexity, which is roughly going like the square root of the total amount of data. And this is essentially using the principle that you can ignore some of the qubits and in the original QROM and output data for every possible value of the remaining qubits. And then at the end, which is indicated by controlled swaps here, that the controlled the thing here with the like the X's and the control the filled in dots indicating controls, that's just a controlled swap. And the controlled swap is for swapping data into the right location. This saves you toffolis at the expense of using more ancilla qubits. And I'll just keep an eye on the time. I'm running out of time a little bit. I might skip over the single factorization, double factorization, go straight to the tensor hypercontraction, because the general idea of all of these procedures is to give a more compact representation of our Hamiltonian. So here we've actually written things in. Is there a question there? I'll just continue. So there's VPQRS. This is much the same as the HPQRS of before, except it's slightly different because we rearranged the A's and A daggers. So that's not really an important difference. The important thing is that this is, again, a set of values which we want to generate. And what we can say is we're going to have a chi and a zeta. Each of these on its own only has two indices. But if we're contracting by summing over the mu and nu, that's actually going to give us this VPQRS. But because each of these things on its own only has two indices, it's roughly going like n squared parameters instead of the n to the 4. Now, the sum over mu and nu is up to m, which is typically larger than n, but still roughly proportional to n. And another point here is that sort of your number of lambda values you would expect to be scaling like this, which might be larger than what the number of steps should scale like the lambda, which might be slightly larger in this representation. So to improve on this, what we did was use I'll quickly mention the second quantization, where you have representation in terms of strings of Pauli operators. So you take your annihilation and creation operators and use sums and differences of them to construct these gammas, which are what's called Majorana operators, which are still anti-commuting but unitary. And these can be represented as strings of Pauli operators when we're representing each of the orbitals on individual qubits. And then the number operators are just going to be like a identity minus z over 2. So what we have with the individual annihilation and creation operators can actually be turned into these z operators when we do and I've actually skipped this is a shorter set of slides here. There's a slide that I've skipped where I was talking about actually rotating into a basis according to these chi's. So essentially what you can do is to essentially take these chi's, because you see you have a sum over chi p and an a dagger p, and you can regard that as like a rotation of the basis of orbitals. But this is going to be slightly different rotations for each of the individual mu's and nu's. But because this is all done in superposition, it's acceptable to do that, even though if you were to try to do all of this at once, this would actually be non-orthogonal orbitals, which doesn't quite work. But anyway, we're able to do these rotations of the orbitals so that this a dagger A then becomes just a number operator on this new basis. And then it turns into something with a product of two number operators. And then the number operators are getting replaced with these z operators according to this representation. And then that is giving us quite a nice behavior here where you have these unitaries, which are the things which are rotating our individual bases of orbitals for the individual mu's and nu's, and we end up with getting a overall amount of data which is reduced, and this rotation of the basis also ends up reducing the lambda value quite nicely as well. And if you remember before in the complexity, it depends on the lambda value and it depends on the amount of data. And if you're able to reduce the lambda value and the amount of data at the same time, then that's going to give you an efficient algorithm. And the overall complexity that we end up getting for the case of FOMOCO, which is relevant for biological nitrogen fixing, ends up looking like about 5 billion Toffolies for a set of orbitals by Ryer et al. A more complicated set of orbitals for FOMOCO needs 32. But both of these are actually beating the best prior work, which was from von Berg et al., which was 10 billion Toffolies for this set of orbitals, or actually 64 billion here, which is actually slightly more than using our sparse method, but still our method with the tensor hypercontraction is giving the best complexity regardless of the set of orbitals that's being used here. I have a couple of slides here that's talking about schemes for reducing the number of qubits that are needed. I'll just skip over that and say a bit about the plane wave basis, since we're running out of time a bit here. Now, in the plane wave basis, essentially what you have is a set of plane waves which are describing your orbitals, and you can have a set of plane waves which are corresponding to particular momenta of the electrons, and you can also talk about a conjugate plane wave basis, which is a bit like sort of physically localized positions, but it's not quite the same as if you were just saying we're going to describe it as an electron at a particular position. And in this scenario, you can actually get a complexity, get a representation of your Hamiltonian, which looks a bit like this, where you have these parts here for kinetic nucleus electron and electron-electron interactions. And these have a nice feature in that the amount of data is significantly reduced. We had an earlier paper which was talking about this, but we can further improve things by essentially calculating things on the fly. So in first quantization, rather than using individual qubits for each of the orbitals, which would be very inefficient here because we now have very large numbers of orbitals, we're actually going to be recording momentum for each of the electrons. And we're also going to be anti-symmetrizing these states to give the anti-symmetric property of electrons. Now, the Hamiltonian is now going to be representable as a sum of unitaries. So this is a rather complicated expression, but the nice feature of it is that each of the individual parts here with the weights is something which is calculatable on the fly. You don't need to classically pre-calculate it. It has this 1 over k nu squared here. That's in common between the second term on the first line and also the term on the second line. And this is now a weighting which is going to need to be prepared in the quantum algorithm. And we want to prepare it on the fly. Now, this k nu, this is something that's proportional to the nu, which is just sort of vectors of integers that we're preparing over. And the amplitudes we want are going to be the square root of that. So it's going to be proportional. So like here we have a 1 over k nu squared. So the actual amplitudes in the state preparation is going to be going like a 1 over norm of nu. So this is like the norm here is just the length of the vector. Okay, so when you want to prepare states with weightings, there's a particular trick that you can use. This was originally invented by Grover, where you can do an inequality test. In our procedure, we use an inequality test. In the Grover procedure, you be using, say, a rotation on an ancilla qubit. And so then in our modification, we use an inequality test, and then you have amplitudes which are proportional to this, but with sort of an overall amplitude for success, which is low. And then Grover's procedure was to use amplitude amplification to get the actual state that you want deterministically. And we do the same thing except using an inequality test. But still, if we have a 1 over nu, the amplitude would be quite small. And so what we have then is a trick which is putting some initial weights on this thing. And that's what this nested boxes are indicating. So this is in the 3D space for this 3D space of nu values. We want to start with a larger weighting in the center box, a smaller weighting in the box outside of that, a smaller weighting in the box outside of that, and so forth. Now, when you're doing the inequality test, instead of, say, doing an inequality test between 1 and this 1 over length of nu, it's going to be scaled according to these boxes. And the overall probability for success is roughly 1/4. And what that means is, well, it's an amplitude for success of about a half, which means you can use a single step of amplitude amplification to prepare this state. Whereas with the original types of proposals, you'd be needing to use many, many steps of amplitude amplification. So when we use that, we can do this state preparation for the Hamiltonian in the linear combination of unitaries for plane waves in an efficient way. And the complexity of that state preparation is only going logarithmically in the total number of orbitals. So that is very useful for these quantum algorithms. And we can also do interaction picture simulations in this scenario. So this is something that Lowe and Weeb were proposing, and we proposed an alternative version, which was essentially swapping around the whether it was the kinetic or potential term we were rotating according to the picture of. So the complexity that they gave in their work was roughly going like the number of orbitals to the power of 2/3, whereas with ours, if we use our procedure, we get a complexity that's going like number of orbitals to the power of 1/3, though it is multiplied by a number of electrons squared, if I remember correctly. So then in our further work, we introduced a whole stack of further improvements. So we actually took the interaction picture and cubitized that to construct something where instead of actually generating the time evolution, we were just doing the phase estimation on that cubitized operator. We also worked out a separate register with the total kinetic energy, which was just updated every time we did the block encoding of a potential energy, which can change the kinetic energy, and then we were doing evolution according to the kinetic energy using that kinetic energy register. We also did better discretization for the time integral, and for the cubitization, we also used a bunch of improvements, and I'm keeping an eye on the time and trying to keep this to an hour. The overall resource estimates that we ended up with looked like this. So this on the left, the top left is the important part for the cubitization. The top right is important for the interaction picture. Now, because it's not really known how many orbitals you'd need, what we've done is actually computed things for a whole lot of different scenarios. So the horizontal axis is eta, which is the number of electrons. So starting over on the left, it's only 20 electrons. Then what's indicated by the different lines is different values of delta. So this is essentially corresponding to a different density of the orbitals. So the different deltas roughly corresponding to different numbers of orbitals. Now, the top ones here, and yeah, so this is circled to the top ones here. You can see over here, it's roughly 10 to the 15, and over here, for the interaction picture, it's significantly less than 10 to the 15. So you're actually getting an improvement for the interaction picture. But for all the rest here, you're actually getting better results for cubitization, which is a bit of a surprise. And the numbers of Toffolies where you actually get an improvement for the interaction picture is sort of on the order of more than 10 to the 14. So that's, remember, let's say 10 to the 9 is a billion, 10 to the 12 is a trillion, and 10 to the 14 is really getting into sort of something that's not realistic for foreseeable quantum computers. It would need very large quantum computers and much higher gate rates than what's anticipated. But if you're looking at sort of the lower left of these, and it's maybe 10 to the 10 Toffolies, and that's maybe about 10 billion Toffolies, which is something that might take a day or so on a quantum computer. So, and as well, sort of the parameters which are indicated up the top here, that's sort of indicating a larger resolution for than you would realistically be expecting for these things. So sort of the expectation here is that even though the interaction picture is sort of a more advanced way of doing the simulations, it doesn't really beat the cubitization. Anyway, so we're just on the hour here. I have a conclusion slide, which is summarizing the things I've just been telling you. Since we're on the hour here, I think rather than reading over this, I think I'll just conclude and give people the opportunity to ask questions. Thank you. So does anyone have questions?
Yeah.
Yeah, I have. Oh yeah, sorry, Abhishek, you can go first. Yes.
Okay. Well, I have a question that can we adapt that for the Hamiltonian simulation? Can we adapt the truncated Taylor series method for the time dependent cases?
Mm-hmm.
So, is there a way to adapt the truncated Taylor series method for time dependent Hamiltonian simulation?
Yeah. That's exactly what I was talking about. So using the Dyson series. So that's this one here. No, there we go. So this is how you're doing it for the time-dependent case. So you're needing to discretize the integrals over time here, but otherwise it's very similar to the Taylor series.
Okay. Thank you.
Okay, so I have a question on the tensor hypercontraction slide.
Yep.
Yeah, the idea is very, very interesting, but I was just curious to know what is M and how we choose the chi's.
That's a good question. So the N here is going to be the number of orbitals. So this is given by some classical procedure for choosing the orbitals. So that's actually not a trivial thing. So there's two cases I mentioned before, the Raya and the Lee orbitals, which were sort of two competing scenarios. And then to work out the chi's and the zeta, this is again something which is quite complicated, that's done in some classical pre-calculations. So the quantum chemists have some code to work these things out. And
Okay.
you can also do sort of some choices of the value of M by, say, doing classical estimation of energies with based on various truncations, and see sort of which ones are going to give you answers which are sort of within the accuracy that you're aiming for.
I see. Okay. Thank you.
Yeah. So any other questions? Does it tend to be something you have to get expert quantum chemists to work out for you? It's not actually my area.
Is there any question on the YouTube chat box, probably?
Just a moment. I couldn't see any questions, but I can just. No, I don't see any questions on YouTube.
Okay, so anybody else has any other questions amongst the audience?
One last question. So in one of the slides that you showed, where you were talking about the complexity of Toffoli gates.
Yep.
Could you just go to that picture? I was just curious what those numbers were that were beneath the. Yeah. So what are these epsilons? Epsilon.
The epsilon there is for the error level. So this was from a paper of Craig Gidney and Austin Fowler, where they were actually explicitly working out how to do so the CCZ is the Toffoli, the Toffoli magic state factory, and it's simplifying things over the previous cases, and also that epsilon is just sort of the error level. So you'd expect if it's say 5 by 10 to the minus 11 error level, you can do maybe 10 to the 10 gates before you're swamped by noise.
I see some kind of an error estimate for those many Toffolis that you put in.
Yeah.
Okay.
So the error level tends to depend on the code distance. So when you're talking about the surface code, you tend to have a number.
So you have surface code in your mind. So okay.
Yeah. So these funny diagrams are indicating various braidings in the surface code. Okay. Typically, what it's indicating, if I recall correctly, is sort of you'd have time going from one plane to another plane, and all of these they sort of square pipes are indicating the qubits being braided around each other.
Okay.
Mm-hmm.
Thank you. That was a very nice overview. The oral talk was very good. Thank you.
Thanks.
Any other questions from the audience? So there's a question on the chat box. Dominic, can you see the...
Do we have any Q-drift kind of alternative for a time-dependent Hamiltonian? Yes. So we did talk about that in one of our papers for doing a randomized product formulas. Trouble is that when you look at actual numbers of gates that you would need, it does tend to be more costly with the Q-drift. So it doesn't really seem to be competitive as far as we can tell with the other methods that we've worked out. So we have been looking at what other ideas for randomized product formulas to try and get better performance. But it's still ongoing work to see if that actually can outperform things that we've already done that I've been describing here. Another, yep, okay.
Any other questions? Anybody else? All right, there seems to be no more questions. Dominic, thank you very much for the talk. Wonderful talk.
Yeah, thank you.
I hope everyone enjoyed, and of course, we look forward to having more talks from you in future. And if you're visiting India, do visit us at some point, our center, and it will be a pleasure to have you here. All right, thanks for the talk again. Goodbye.
Yep. Bye-bye.